Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we'll be going over acid strength. We're going to be going over weak acids and strong acids. As you can tell, I have not shaved in a while, so don't be surprised if this goes away. And plus, it's kind of casual, so I'm wearing a hat because um, I have a hat here day. Anyway, so I'm glad you could join me. So again, in this video, we're going to start with acid strength. So what do we mean by acid strength? Well, what we mean by is like how much it ionizes in water. And right off the bat, I want to kind of distinguish between two terms that a lot of times it's easy to confuse, or you interchange them when you're not supposed to. They're technical terms. Um, and they mean slightly different things. So when we're talking about acids, when we throw them in water and they dissolve, we use the word ionize. But when we're talking about what do you call them? Ionic substances, right? Ionic salts, sodium chloride, magnesium nitrate, things like that. When we put those in water and they dissolve, we don't use the word ionize, we use the word dissociate. And the reason for that is because ionize means you're making ions. So things are becoming ions uh, in the process. So we don't use that to refer to the dissolving of ionic compounds because they're already ions. They're not becoming ions, they are ions. The only thing that happens when you put an ionic substance in water and it dissolves is the separation of the ions, the cation and the anion, the positive and the negative, right? And so you're not ionizing them technically, you're dissociating them. So dissociate means to kind of separate, to pull apart. So when we're dissolving ionic substances in water, we say dissociate or dissociation. But however, with acids, they're molecular acids, meaning they're molecules. They're not ions. So before you dissolve them in water, HCl, let's say it's a gas, HCl gas is a molecule. It's not the hydrogen and the chlorine are not ions. They're bonded together in a covalent bond. However, they're kind of special in the sense that when you do put acids into water, the water molecules will pull them apart and they become ions. So you are ionizing them. So that's a distinction between what we say regarding acids as opposed to what we say regarding ionic substances. So acids, we will use the word ionizing or ionization. Um, uh, but with salts, we'll be using the word dissociate. So hope that's clear. And I might accidentally go back and forth, and I'll correct myself when I can. um, so acid strength. What we're talking about with acid strength is like how much the acid ionizes in water, right? So how much H plus is given off, right? So either a lot of the H plus is ionized, right? So is formed when you put it in water, or very little of it. So the stronger the acid, the more H plus that is ionized. So the more the acid ionizes when you put it in the water, the stronger the acid. The less it ionizes in water, the weaker the acid. So here, a strong acid, what we mean by a strong acid is a strong electrolyte. And electrolytes, again, are substances that become ions or produce ions in water. So electrolytes we call them electrolytes because they're positive and negative ions. It allows electrical current to go through the substance. So practically all acids, acid molecules ionize. Practically all of the acid molecules ionize. What does that mean? It means when you put a strong acid in water, almost all or practically every single molecule of the acid ionizes. So it means they break apart into ions. Okay, so that's what we mean by a strong acid. A strong base is the same idea. It's a strong electrolyte. What does that mean? It means that practically all of the base molecules form OH ions. So either through dissociation, right? So a lot of strong bases are salts. They're ionic compounds. So like sodium hydroxide, NaOH, that's a salt. Sodium plus ion, hydroxide, negative ion. So those are going to dissociate in water, or they react with water, right? So a weak acid is a weak electrolyte. That means that only a small amount, very, very tiny amount of the molecule breaks apart or ionizes into ions, right? So when you get a weak acid, you get this double arrow going on. So another distinction to make when you're like drawing your equations for a strong acid versus a weak acid is strong acids go pretty much only one way. So they're going to break apart 100% or very, very close to 100%, practically 100%. So for example, if you throw hydrochloric acid into water, HCl, all of the HCl is going to break up into H plus and Cl minus. So it's an arrow that goes in one direction, right? The arrow points in one direction. Same with strong bases. With weak acids and bases, it's a double arrow. So again, this E here should be a double arrow. And that means there's an equilibrium. There's a reverse process, there's a forward process. And most of it is going in the reverse direction, meaning that very little of it is going to dissociate or ionize in water. So you've got that double arrow going on. So you've got the forward process going on, you've got the reverse process going on. And so both of those are happening at the same time with a weak acid or a weak base. So again, a very small, tiny percentage of the molecules actually ionize for a weak acid, or and for a weak base, same idea. It's a weak electrolyte. Only a small percentage of the base molecules form OH minus ions, and so this is either through dissociation or reaction with water. And again, this E here should be a double arrow representing an equilibrium of sorts. So let's move on. So let's talk about strong acids. So again, strong acids, they donate practically all of their H plus ions, right? So pretty much all of the H plus or hydrogen, the acidic proton in your acid is ionized or released or given off. And again, we call these strong electrolytes. Again, electrolytes are substances that form ions when you put them in water. So basically, all of the hydrogen that is released is supposedly picked up by water molecules. Remember, we don't have H plus ions or individual protons floating around in water. It's all in the form of hydronium ions. So the concentration of the hydronium ions should equal the concentration of the strong acid you started with, right? So for example, and this applies to your monoprotic strong acids like HCl, HBr, and so on, HF, or actually HF is a weak acid. or HBr. So your strong acids are the concentration of them is going to equal the concentration of the hydronium ion in solution. So remember that. So if I have 1 molar solution of hydrochloric acid and I put that in water, that means I'm going to end up with 1 molar solution of the H plus ion, assuming equal volumes, which yeah. So 1 molar, okay, so let me rephrase that. So a 1 molar solution of an acid means that you have 1 molar solution of H plus ions, which means you have a 1 molar solution of hydronium ions. Hopefully that makes it clearer than what I said before. It wasn't quite right. So the species in brackets, so when you have square brackets here, that means the molarity of that species. So the molarity or the concentration, and molarity is a measurement of concentration. As you learned probably before, is in another video we talked about different sorts of concentrations, different measurements of concentrations, and molarity is one of them. So when you see square brackets, we're referring to molarity. Okay, and so what you can see here in the picture is that you have HCl, and all of the HCl is broken up. You don't have any HCl together, and all the hydrogen here is picked up by water to give you the hydronium ion. So again, here's another picture representing what's going on here. Okay. So here are the 6 strong acids. You should memorize these strong acids. They're very, very common, very important. So again, most of them are the binary acids that you had learned to name, right? So you HCl, HBr, HI, and then you've got some the oxy acids, right? So you have nitric acid, you have perchloric acid, and sulfuric acid, which is a diprotic acid. So these 2 hydrogens can ionize. So this one will produce double the amount of H plus. So 1 molar solution of H2SO4 means you have a 2 molar solution of hydronium ions. Okay, so again, weak acids, when we're talking about weak acids donate a small fraction of the H plus ions. Most of the weak acids do not donate, weak acid molecules, most of the molecules do not donate their H plus to water. Very, very little. So much less than 1% ionize in water. So very, very little of the molecule is going to ionize and donate its proton. So here you can see that the molarity of the weak acid, right? So if you're looking on the bottle for the molarity of the weak acid, that means that the concentration, whatever that concentration is read on the bottle, the hydronium ion is much, much less than that because it's not ionizing very much, right? So the amount of H plus or H3O plus that you have in solution is going to be very, very tiny compared to the actual molarity of the weak acid itself. And you can kind of see in the picture here that H plus, there's little H plus, like so you still have HF stuck together. So the molecules are still together. They haven't ionized. Most of it is together. And you get like a couple of molecules that came apart and you form hydronium ions. So that's a good indication of a weak acid, or a good representation of a weak acid. And here are 6 of your most popular weak acids. So you have hydrofluoric acid, acetic acid, formic acid, sulfurous acid. So don't confuse that. Sulfuric, sulfurous. Sulfuric is H2SO4. Sulfurous is H2SO3. So sulfurous acid is a weak acid. Carbonic acid is weak. And then we have phosphoric acid is weak, and that's a triprotic acid. So all 3 of these are going to be released. Okay, in the next video, I will continue with strengths of acids and bases.